Let's revisit the definition of a derivative. If you'll recall, we start by thinking about the graph of a function. And so I'm just going to graph a function here. And what we want to do is we want to think about, we're interested in the derivative at this point x. So what we're going to do is we're going to add a little bit to that x. So we'll call that delta x. So see, we're just adding just a little bit. We're moving over to the right a little bit, so we're adding a little bit. Delta x just means, of course, change in x, right? So what we can see is, if we look at our function, we can imagine 2 points. The first point, right here, would be x comma f of x. And the next point would be x plus delta x, comma f of x plus delta x. And we can imagine the secant line that connects those 2 points. Remember, that's called the secant. And when we're talking about the derivative, we're trying to go from a secant to a tangent. So what we're going to do is we're going to make delta x smaller and smaller until we're actually right on top of, the 2 points are right on top of each other, and we no longer have an actual difference. So what we're saying is, in calculus terms, we want to take the limit, as delta x approaches 0. And remember, we're looking for the slope of that tangent line. And so we deal with the slope of this secant line, which we can see we take y minus y. So on top we get f of x plus delta x minus f of x. And so change in y divided by change in x. And of course the change in x is just delta x. Okay, and this is what we call the limit definition of the derivative. I will also point out, I've mentioned this before, but just to remind you, very often instead of delta x, a lot of textbooks and sometimes the AP test, in fact often the AP test will call that h instead of calling it delta x. Can be a little less confusing in my opinion if you call it h, but delta x is more descriptive because we know that delta x means the change in x. And so as we squeeze that delta x down to 0, we move from a secant line, from an average rate of change, to a tangent line, to the instantaneous rate of change, or the derivative. Now, the way this shows up usually on the AP test is that they will give you a limit already set up. And they'll say, hey, we want you to take the limit as h approaches 0 of this big, long function. Now, there's no reason that we could not go ahead and algebraically manipulate this. In fact, we could say this is the limit as h approaches 0. I'm just going to take x squared plus 2xh plus h squared. I just FOILed out that x plus h squared, and then I'm going to distribute the 2, and so I've got plus 2x and plus 2h, and then I'm going to distribute the minus. I've got minus x squared, and I've got minus 2x, and this is all still over h. And so once I do that, notice that I do have an x squared here minus an x squared here. That goes away. Goes to 0. I have a 2x and a minus 2x here, and that goes to 0. And then finally I see that everything that's left up here that didn't subtract to 0 still has an h in it. So I can divide out the h on the top, so I can keep going. I can say this is the limit as h approaches 0, and on top I'm going to factor out the h, and so that leaves me with 2x and plus h and plus 2. And then I still have the h in the denominator. Conveniently, those h's cancel out, and I get the limit as h approaches 0 of 2x plus h plus 2. It's now safe to plug 0 in for that h, and I can evaluate this limit, and I can see that this is 2x plus 2. Now, no reason you can't do all of that algebraic manipulation. However, now that we know more about derivatives, we can look at this and we should be able to say that, let me get some of this out of the way here. What we should be able to do here is recognize that this whole limit that we're being asked to evaluate here is really just the derivative of x squared plus 2x. Now, obviously we can do the limit, we just did it, but we know lots of rules now for taking derivatives, and all we have to do then is say, well, I know that the derivative of x squared is 2x, and I know that the derivative of 2x is 2. And so I can just use my power rules, and I can get the exact same answer without going through all that nasty algebra to evaluate this limit. So what they're really asking you to do here is recognize this as the definition of the derivative so that you don't have to do all of that algebraic manipulation to solve it. So let's look at one more problem that would work like that. So I look at this problem where we have the limit as delta x approaches 0 of sine of x plus delta x minus sine of x divided by the delta x. Now, the algebraic manipulation here and trigonometric manipulation actually gets pretty ugly. We have to use our sum identities for signs so that we can split some things up. Really don't want to deal with it, and that's not what they expect us to do anyways. What they expect us to do is say, oh, this looks like the definition of the derivative, so I know I'm taking the derivative of something, and I see that it looks like, and usually you can just really, the easiest way to see it is what's after the minus. And what's after the minus is sine of x. And so I look at that and I say, well, that's great. I know what the derivative of sine of x is, and I just say, well, that's cosine of x. And so very rarely, if ever at all, would they ask you to actually do a derivative by definition. More often what they're going to ask you to do is recognize that definition and then use your rules for derivatives.